Welcome. This question says an 80 kilogram mass is located at the origin. Determine the potential energy difference when a 5 kilogram mass moves from a point defined by 0I2J 0K meters to another point defined by 8I plus 0J plus 0K meters. So basically we have a if you like a host mass that's setting up a gravitational field, and then we have a smaller mass, and we're picturing it being inside the gravitational field created by the host mass, and we basically move it to a higher altitude. Yes, it's pointing along the y direction to begin with, and at the end it's pointing along the x direction, but we don't really care about the direction. All we really care about is the altitude in these problems. So we're just imagining, it goes up higher into the air, and so I expect an increase in gravitational potential energy, so I expect my change in gravitational potential energy to be positive. So let's visualize a little bit better. So we have here, and we have 80, and then we start off, if you like, 2 clicks, 2 meters up here. We start off with our 5 kilogram mass, and then 1, 2, 3, 4, 5, 6, 7, 8. We end up here with our 5 kilogram mass, and the path taken doesn't matter. All that matters is we go from a low altitude to a high altitude. I need a principal relationship, and my change in gravitational potential energy is equal to minus G m1 m2, and now we have 1 over r final minus 1 over r initial. So there's my relationship. I've learned the relationship. Negative sign is there so that when you get increases in altitude you get positive sign. I say my delta UG, my change in gravitational potential energy, is equal to minus G. We're going to leave the G in there. This is 80, and this is 5. And then we have 1 over, this is 8 meters high, so 1 over 8 minus the initial was only 2 meters high, so 1 over 2. So we have delta UG is equal to minus, I'm going to leave my base numbers in there, so it's 80 and 5. And then this would be 1 over 8 minus 4 over 8. 4 over 8 is the same as a half. So delta UG is equal to minus, got my minus G last time, minus G 80 times 5. Now this is going to be minus 3 over 8. 1/8 minus 1/2 is minus 3/8. Almost there. The change in my gravitational potential energy is equal to, well, minus and minus are going to make plus. And 8 goes into 80 10 times. So 10 times 5 is 50 times 3 is 150. So that's going to be plus 150. We've still got the G in there. We didn't bother making the numerical value for the G part of our calculation. And then of course we need units, and our units would be joules. So, and sometimes I like to put brackets around that so that I can distinguish between the actual numerical answer and the units. And so if I look on here, there we have it. And we can see it's still, it's a nanojoule. Well, it's about 10 nanojoules. It's 10 nanojoules of energy. You imagine taking a 5 kilogram mass in space near a 80 kilogram mass, and you move it from 2 meters out to 8 meters out. And basically, how much work did your lifting force have to do? And it would be 10 nanojoules, a tiny amount of energy. And there we have it.